Sometimes whenever you're looking at problems, you're not given just a simple x component and y component. Instead, you're giving equations for the x and the y to actually deal with. Now, in math, we would call this parametric equations, where we have both an x and a y in terms of t. So instead of solving for just an x number here, the x position is actually changing according to time. If we're going to call, let's say, this the positive x, there's the positive y, maybe this thing is moving out and then moving back, or maybe it's moving back and then coming back forward according to time. And then the y-axis, its component is changing also according to time. You can see it starts out negative with a negative acceleration and then a positive initial velocity, so it must start out going up and then eventually start coming back down. And the changing of those two components and the x and y axis actually gives us the motion of the cart. So apparently in this case we're looking at Dune carts, something like this, and there's a 10-hour race that we're going to go on here, and it asks us in the first question here just to describe the motion of the Dune cart. So first thing I need to know is what's happening in the beginning. Well, in the beginning, looking at just the equation in the x, looking at the equation in the y, both of those have a positive initial velocity, right? And in the spot of the acceleration here, there is a negative acceleration. This would be 1/2 a, is what those would equal if you're thinking about your kinematics. But I'm not done yet. I need to find, if I'm going to graph it out and be able to describe it with words. By the way, whenever you do these things, please graph them out. Graph out the individual equations, right? Graph out the individual equations, and for parametrics, then you're going to want to plot those things on just an XY graph. You're going to want to get rid of the time and see where is it going here in the XY. So to do that, I need to find the maximum points in the x, the maximum point in the y, if there is a minimum point. If it wasn't just an x squared, we would need to solve for that. And also if there are any inflection points. The maximum points, if this is a position graph, will tell me where the velocity is 0. We have reached our maximum displacement. Our inflection points will tell us where the acceleration is 0. The inflection point would be the second derivative. It'll tell us where the acceleration is 0. In other words, the acceleration is changing at that point in time. Maybe we're going from accelerating to decelerating. So let's start out by working in the x-axis and actually solving for my maximum point. Now I have the derivative, so we can set that equal to 0, make the velocity there at the point I'm looking for 0, and solve for the time at its maximum displacement. And I come out with a time of 5 seconds for the maximum displacement. Of course, now I need to take that time and substitute it back in. Let me point out the reason we're going to do this. We're finding where the maximum position is. We're going to find where the inflection points are. Inflection points would tell us, by the way, we've already kind of cheated here. We have a graph of this function, but that's what we're actually trying to build. We're trying to build this graph here so that we can describe what's happening with words. So we'd be able to plot now the time that occurs at. Now we need to know the height, the position that it's going to occur at, because I know now what time the maximum is going to occur at. The inflection points would tell us if the acceleration is changing. Maybe it starts out with a positive acceleration and then curves off and then comes into a deceleration there, kind of like an S or a cube, as you might know. So we need to know inflection points. We'd also want to know the zeros. Where does it actually start and stop in the x-axis? So we'd plot the we'd set x of t equal to 0 there too to solve for those times. But for now, let's actually find the maximum position. And we find our maximum position here is 137.5 kilometers. Kilometers I'm using because if you look at the y-axis here on both of those for position, for the x and y position graphs, we're using kilometers for the race that the Dune carts would be moving over. All right, let's now check for changes in acceleration. We already know there won't be one. This is a constant acceleration. We could recognize that off the equation, but let's check it anyway and find our inflection points. We already found the velocity equation. We took the derivative of the position equation, so here's the velocity equation. We set that equal to 0 and substitute back in to find the maximum velocity. So now let's look at, maximum position. So now let's try to find our maximum velocities, if there was one. That would indicate a change in acceleration. So whenever I take the derivative here and I come out with the acceleration, so d dt, this entire equation here, my acceleration turns out to be just -11 there the entire time, a constant acceleration, so there is no way I can maximize that. There is no substitute 0 in and solve for time there, meaning that there are no inflection points. The last step that I would like to be able to do here, and I'm actually not going to bore you with this mathematically, the last thing that you would generally like to do is, now that I can plot, which I would come over here and I'd plot here's the time and here's the distance that the maximum would occur at, and I'd plot that, as you can see on this graph. If I had any inflection points, I'd plot those, but here I don't have any, so there's nothing to plot, and telling me that I have a smooth curve. It's not going to S, if you will, in it. I'd like to go ahead and substitute 0 in for the position so I can find where it intersects the x-axis, but I'm not gonna go through that. It's already here on the graph. Now, after you're finished sketching a x graph, a x time graph, we would need to go through and redo for the y so that we could sketch our y position graph, knowing where the maximums are, knowing where the zeros are, knowing if there are any inflection points, changes in acceleration. I'll do that rather rapidly for us so as to not just re-show what we've already done. And we come out with our y maximum, which of course lines up with this maximum point, as if this graph wasn't here and we were sketching it out. So I'd put a point at 16.67 seconds, time in the x-axis, and then 208.33 for the y position on the y-axis. Take the second derivative to look for inflection points. And I find instead that the acceleration to be a constant, negative 1.5 kilometers per hour squared, so there are no inflection points. It's actually a constant acceleration the entire time, negative 1.5 kilometers per hour squared. So after I have that done, we can actually come back up here. Once again, won't bore you with the math. We would substitute in 0 for our y so that we could find the times where it intersected the y-axis. That'd let me plot it because I'd have 3 points. I'd have where my y equaled 0 times, and I'd have my maximum and no inflection points, and here's smooth curve right there. Now, of course, this is all the math with it, which is good to be able to do, and you should be able to do that, but you could also use your graphing calculator and just simply plot it out to try to get an idea what's going to happen. And unless the problem specifically says you need to actually be able to do the math to where you're finding the first derivative to find the maximum positions, second derivative to find any inflection points, changes in accelerations where it would S, if you will, and you're putting in zeros to find where it intersected the zero axis, the x-axis, you could just simply actually plot it on the calculator. Let's take these two graphs now and actually plot out what's going to happen on an xy coordinate. First thing that I need to point out is this race is only 10 hours, so we can actually cut off these graphs at the 10-hour mark. So here's 10 hours, and then on the y, here's 10 hours on the x. So the y graph is what we can see. For my y motion, I am going to, if you will, increase the entire time. The entire time I'm going to go up in the y, but my steepest increase in the y will be in the beginning, and then towards the end it'll actually be a lot less. In the x, it looks like we're actually going to turn back. We're going to start at 0, and we're going to turn back to 0. But the first point I know I can plot is 0, 0. Now I can say that at 5 seconds here, let's get the little laser pointer, at 5 seconds I was at my maximum x, and at 5 seconds I was somewhere up here in y, so I'm just sketching that out. So that's going to be maybe somewhere over here, right? And then at 10 seconds, I'm back here at 0x, I'm back here, so x needs to be 0, so I came out in the x-axis, I need to come back. But at 10 seconds, I'm still increasing in y, so it's going to be somewhere, let's say, up there. And if I'm going to smooth curve this, it looks something like that, maybe, for the shape of this race, or the shape that my Dune buggy would end up going in. If I were describing this in words, I could do it one of two ways. I could either describe the x and the y separately. In the x-axis, we were decelerating. We started out with a large positive initial velocity. We decelerated, reached a maximum velocity at 5 seconds, or excuse me, a maximum position at 5 seconds, and then we negatively accelerated all the way back down to our starting point at 10 seconds. In the y-axis, we started out with a large positive velocity, but we slowed down the entire time until the end of the race, 10 hours. Now, if we instead want to describe it on a north, south, east, west, on a compass here, we make our y-axis the north-south and east-west the x, then you can actually look at what's happening shape-wise. It looks like this race is going to be moving northward the entire time. So my car starts out with either a slightly northeast angle that eventually curves to where we're going just north at the maximum x, and then it begins to curve back, taking on a northwest version all the way till at the maximum y. It looks like we're going, because we'd be going 0 in the x, we'd have a purely westward direction. All right, let me restate once again what you're going to end up doing here to actually get the graph. It would be good to use your graphing calculator to get both graphs of each equation. You could even use your graphing calculator if you know how to graph a parametric to actually graph the parametric curve. After you do that, then you're going to, if you graph it, if you actually need to use actually show the math, there are a few steps. Step 1, take the derivative, so set equal to 0, so you can find the maximum position in each of these. Step 2, take the second derivative so that you can find any inflection points if there are, if it's going to S-curve anywhere. Step 3, go ahead and set your x or your y equal to 0 so you can find at what times it intersects the xy axis. That'll let you graph each of those individually. Then you can look at the domain. We set this to a 10-hour race, and that'll let us graph the actual parametrics and allow us to talk about, using these three graphs, the full motion of the object.